Hi there. We want to talk today about molecular and ionic compounds. This is it's from chapter 3, but it'll be on the fourth exam that we're doing. So this is for the last exam we'll have this semester. So what we're going to do is talk about these two different kinds of compounds, ionic and molecular or covalent compounds, make some predictions about what type of compound will form, and determine the formula for some simple ionic compounds. So let's see, I'll make this big. We can go through that. When you're forming compounds, things react to form the compounds, and the thing that changes is not the nucleus but the electrons right here. So chemistry is all about the electrons. If they're gained or lost, that's going to be an ionic compound. If they're shared, that's going to be a covalent compound. Sometimes you can have both going on in an example. We'll see some of those. So here's a picture of a sodium ion. The sodium ion is on the right. This is the ion, and the sodium atom is to the left, and you can see that the sodium ion has less electrons, 10 instead of 11, and as a result it's smaller. It's got a smaller volume, and it does have a positive charge there. Now, the great thing about the periodic table is it tells us lots and lots of stuff about how elements are going to react, and the atoms of those elements are going to react. And we can predict if something is in the first group on the periodic table, group 1, so that's lithium, sodium, potassium, etc. Those guys are always going to show up as a +1 charge. If they're not just the metal itself, they're going to lose one electron and form a +1 charge. Positively charged ions are called cations, right? Cations. Make sure we know that term. And then if you go to group 2, so that's things like beryllium and calcium and things like that, magnesium, they always form a 2+ charge. So that's pretty easy. Group 1 +1, group 2 +2. Now when you look over on the other side of the periodic table, the last group, group 18, is the noble gas, right? Remember, so noble gas is group 18. And what we're going to do is we're going to kind of count backwards from there. So if you're group 17, what you tend to do is pick up an electron, okay, that forms a -1 charge anion, okay. And then if you go back one more group, that's the group of oxygen, you're going to get 2 electrons and form an anion with a -2 charge. So there's some variation of those rules. They're not quite as hard and fast as the group 1 and 2 rules, but those are pretty good, pretty reliable rules in terms of predicting how those things are going to behave. So here's 2 examples. Calcium in group 2. Group 2, it's going to lose 2 electrons. It'd be a calcium +2 ion. We lost the superscript there. That should be calcium +2. Should be up there, and if you look, that has exactly the same electron configuration as argon. Bromine picks up an electron. It's in group 17. That is Br-, and when looking ahead to naming these things, calcium +2 is called a calcium ion. Br- is called bromide. It ends in IDE. That's for a monoatomic ion that's negative, that's picked up enough electrons to get to the noble gas configuration. We use the IDE suffix. So bromine is Br2, bromide is Br-, and that's something to be aware of, those distinctions. Now, if we go back and forth on the periodic table here, as you get towards the middle, things get less reliable, right? It's a good guideline, but it's not a hard and fast reliability. There's some things we know, though. For example, we know copper is either +1 or +2, iron is +2 or +3, tin is either +2 or +4, lead is typically either +2 or +4, Silver is almost always +1. Zinc is almost always +2. And of course, if we write +2 or 2+, those mean the same thing. So there's some things that we know and some things we don't. So this is the table here, and this would be stuff that I would expect you to know, as in memorize this. If you had a closed book exam, which you won't be having in this COVID semester, but if you had a closed book exam, you'd be expected to know these ions. These, as I said, as you get to the middle, these get quite a bit more unknown, I would say. I've seen carbon, the +2, +3, +4, depending on how you do it. Nitrogen has, basically goes from -3 all the way up to like +5 and everything in between. It's very hard to predict how those things are going to do, and also frequently the charges, it gets a little weird, when we step out of ionic compounds and into covalent compounds. We have a way of thinking about the charge, then we call it the oxidation state. So they're just much more variable, but a lot of those are pretty good and hard and fast. Now, in addition to the monoatomic charges we all just looked at, we have things called polyatomic ions. Now, a polyatomic ion has more than one atom, and it's charged. It's an ion. And a special type of them that are quite common are ones that contain oxygens, oxyanions, and they contain oxygen atoms. So here is another table of these, and again, this is a good thing to know. Of these different polyatomic ions. And let me just say that even in an open book situation, or a situation where you have a formula sheet with some of these things on there, you need to practice referring to them and recognizing it. It's kind of hard sometimes on the fly to tell what's going on. For example, many students, if they encounter something like this hydrogen phosphate ion here, HPO4 2-, if they see that in a compound, I'll see oftentimes students will say, well, it's H+, it's P3-, it's O4 -2, something like that, and that's wrong. That's not how that behaves. It's a polyatomic ion. All those things are stuck together with covalent bonds, but the whole thing has a charge on it, so it's ionic. There is sort of a system for naming these oxyanions. We're going to use two suffixes, ate and ite. So we had "ide" before for monoatomic ions. When we've got oxygen involved, you may have learned, I learned in biology, that anything ending in "ate" meant oxygen. Anything ending in "ite" also means oxygen, but not as many. And then there's some prefixes we use, per and hypo. Per means more, and hypo means less. So we'll see that there is a pattern for naming these, which I thought we'd be looking at. So let me just run through that for you. So ClO3- is chlorate. ClO2-1 is chlorite. ClO-1 is called hypochlorite. It's got less oxygen than chlorite does. And then ClO4- is called perchlorate. And so these are very closely related species, but they are quite different. Hypochlorite is in bleach. Bleach, which you may have in your laundry room or something, is about a 3% to 5% solution of sodium or potassium hypochlorite. And of course, you're familiar with bleach probably. If you get bleach on something that you don't want to get bleach on, it might make I wouldn't call it a stain, but we usually say it bleaches it out. It makes it, lose the color there. Perchlorate is something that's so reactive that it's pretty much called the bomb squad if you run across this stuff. Perchlorates are very, very dangerous. Hypochlorite, certainly we respect it quite a bit, but we sell it in grocery stores and take it into our homes. So there's quite a bit of difference here. One of the things I talk about when I'm talking about nomenclature to students is I want to talk about the monoatomic ion of nitrogen. So nitrogen is probably going to be 3 minus as its monoatomic ion. That would be called nitride. Now I'm going to change one letter. I'm going to change that D to a T, and that becomes nitrite. Nitrite is NO2 minus 1. Now I'll change one more letter. That'll become nitrate. Change the I to an A. That's NO3 minus 1. This is why one of the reasons chemistry is hard is that a very minor change in spelling has quite a bit of change in terms of the formula and the properties of something. So you want to be careful about that. Okay, so we said before that if we have electrons transferred and you have a positive ion and a negative ion, that's an ionic bond. And if you share the electrons, that's called a covalent bond. And based on what kind of bonding you have, we call things ionic or covalent or molecular. Sometimes, though, you'll see things happen where you actually have both ionic and molecular, but usually ionic would win out on that. So if you had, for example, sodium nitrate, okay, that's Na plus, and then we're going to have this nitrogen compound here, and I'm going to draw something that you don't know how to do yet. That's a Lewis dot structure, and that is that nitrate ion. Those are covalent bonds there in that polyatomic ion, but these two are held together by ionic bonds, so we would call this an ionic compound. So, and ionic compounds and covalent compounds immediately have some quite different properties. We've talked about that. So one thing you can do easily from the periodic table is figure out what kind of charges you're going to have and what kind of ratio you're going to have between the charges. So if I have, for example, sodium tends to form a +1 charge. If I'm talking about sodium and chlorine, they tend to form a -1 charge, and you've got essentially this thing called the principle of electric neutrality. Which says that they're going to combine, your anions and your cations are going to combine in such a way that the overall charge is going to be 0. They're going to neutralize each other, in essence. And one quick way to generally figure this out, or at least get a start on it, if we think about the number part of that charge, if you take the number alone and you cross those are going to be what we call the subscripts of the equation, or which tell us how many of each type of ion or atom we have. And generally, if we have ones there, we don't write them. We just say NaCl. Now, if we're looking at calcium and chloride, there's 1 there that would go there, a 2 here that's going to go over there, and we wind up with CaCl2. And if you look at the picture of that, that's calcium +2 with 2 Cl minuses there. And if you count up your charges and all that, I've got +2 and 2 -1s. The overall charge is 0. It's neutral. If you have something like calcium and oxygen, oxide, if we cross those, we get Ca2O2, which we then generally go to the least common denominator. So divide both of those by 2, and we get CaO. That would be the formula of calcium oxide. And it makes sense that we got a +2, 1 +2, and 1 -2. So that crossing the charges thing, sometimes you have to correct for that fact. If you can lower those numbers to all to common denominators, then that'll work out. Now, ionic compounds are usually solids. They usually have high melting and high boiling points. They don't conduct electricity when they're solid. They do conduct electricity if they're melted. That's the liquid form. Molten form is liquid form. They conduct electricity in water if they're dissolved in water, and they readily dissolve in water. Generally, we can see that. So we talked about these electrical neutrality and stuff. So this is another example of what we talked about a few slides ago. When you are putting polyatomic ions in there, you do need to remember to keep them together. And you see how we use the parentheses here and this number outside of it to reference the charge there. So this is calcium phosphate, and the way I would read that is I would say Ca3PO4 taken twice, meaning that we take that whole PO4 group. So that'd be kind of how I would say that formula right there. And that 2 goes through the whole thing. So Ca3PO4 2 is equal to Ca3P2O8, where I've multiplied the 2 times the 1 and the 2 times the 4. We don't refer to it that way generally, but if you were looking it up by formula and say an index or something, that might be how you look for it. But we're emphasizing the phosphate ion and that we have 2 of them because we know something about phosphate ions. In molecular compounds, we share those electrons. Again, generally we got neutral molecules, although you can have polyatomic ions that are formed. Usually you're looking at nonmetals, and nonmetals, remember, on the periodic table, a rough outline of the periodic table here. Hydrogen is a nonmetal, and there's a staircase line over here. The other nonmetals are over here. These guys are all metals down here. So usually it's nonmetals and nonmetals. And many of these are gases, so like CO2, CO, N2, O2, things like that are all gases. Low boiling liquids. H2O is kind of not really a low boiling liquid, but it certainly is a covalently bonded liquid. Low melting solids, that might be something like if you have C20H42, for example, is kind of a wax like low melting solid, so those again are all non-metal compounds. Later on, you'll get into quite a bit about how to describe the bonding and the structures of those, but that's more of a Chem 131 topic than a Chem 130 topic.